A warm welcome to you all to the second day of the World Space Week celebration by SSERD. I hope you all learned a lot yesterday from the keynote by Professor Arup, and today we have a keynote on remote sensing. Well, when we talk about satellites, the very next term that we associate satellite with is remote sensing. Though most of us don't know what remote sensing actually is, we kind of, they go hand in hand, the term remote sensing as well as satellites. Today, we're going to be learning more about remote sensing, and to tell us more about remote sensing concept, we have with us today Mr. Awais Ahmad, and it's a great pleasure for me to introduce Mr. Awais Ahmad to you all. He's a graduate from BITS Pilani, and he, along with one of his partners, they started the startup called as Pixxel in 2019, and this startup happens to plan in launching a set of constellation or micro observatory constellations of satellites to observe Earth. Their motto is to see the unseen. So the founder and CEO of Pixxel, Mr. Awais Ahmad, is here with us today to give a keynote on remote sensing. It's a great pleasure to have you, sir. The screen is yours. Thank you.
Thank you so much for that. Hey everyone, it's a pleasure to be here. Before we sort of get into the remote sensing, what we're doing with Pixxel and what are the tremendous applications, I'll just share a brief about myself and what we're trying to do. So, as was mentioned, I'm one of the co-founders of this young startup in India called Pixxel. And what we're doing is building a constellation of remote sensing microsatellites. They'll take images of any geography on the Earth, and we will analyze these images to provide insights in a variety of industries like agriculture, oil and gas, climate change, and so on. Um, just to start off, right, if you look at the screen, this is an image of Earth. This was an image that was taken by the Voyager 1 spacecraft in 1990 as it was leaving the solar system. And when you look back at it, you see, how tiny we are. And if you zoom in a little, that's you, me, everyone else that's ever lived. That's everyone else that will ever live as well. It's like a huge family selfie, so as to say. And what this image did was it galvanized a whole generation of human beings. We saw that we at spaceship Earth are a fragile species, and that we need to take care of the planet. It's a very unique planet. It's the sole planet that we have, and we need to be able to take care of it. And this is what sort of led to the genesis of Pixxel, because when we and this picture also galvanized us, right? And we wanted to look at ways in which we could help the Earth, and we decided we would participate in this competition called the IBM Watson AI X Prize, which stated that you had to use artificial intelligence technologies to tackle some of humanity's problems. And for us, a combination of AI and satellite imagery seemed like the way to go. We were looking at tackling issues such as, like monitoring where and what air pollution or water pollution emissions were coming from. We were looking at tackling pest infestations or crop diseases across the country and so on. And there were multiple different problem sets that came up that we could solve with satellite imagery. So this was a data set that we decided that we could go ahead and tackle problems such as hyper-urbanization of cities, where cities are growing rapidly and unchecked. We need to be able to have ways to be able to plan these as they grow rapidly, or be it the deforestation that's happening in the Amazon or elsewhere, be it the lack of water shortages occurring in the Middle East, or a lack of crop efficiency. The amount of crops that need to be grown to keep up interact with the human population is not something that we're currently achieving, or even dramatic climatic changes that are occurring everywhere in the world. These are the problems that we sort of set out to achieve while participating in the competition. But then like we realized that there were certain issues with the way the images were beaming down, right? One is, if you have seen images of the satellites, be it on TV, National Geographic, or elsewhere, or on the screen right now, you'll see that they're usually the size of an entire room. And they have been very bulky. They take years to manufacture. That takes hundreds of millions of dollars or many crores to manufacture. So it's been a very lengthy, huge process to be able to build these satellites, to go up there and take images of the Earth, to be able to tackle the issues we just looked at. Like take this satellite for example. This was a satellite that NOAA was building in the US. The satellite cost about $300 million to manufacture, and it fell down while manufacturing, and they had to redo it from scratch. So these are the problems that you usually face if you're working on a satellite of such proportions and with such costs. And something happens during the manufacturing process, you have to essentially start from scratch. But over the past few years, there's a revolution that's been coming. It's that satellites are becoming smaller and smaller. The optics, the sensors, the cameras are becoming smaller and smaller, which enable us to do things much more rapidly. So instead of it taking years to manufacture a satellite, instead of it taking hundreds of millions of dollars to manufacture a satellite, and there being risks in terms of what happens to one satellite, it's been changing to build multiple small, inexpensive satellites that can be rapidly manufactured, and you can provide global coverage at a much higher frequency to be able to take these images, right? And multiple companies like Planet and others have done it, and we at Pixxel are also going to do the same. And there's a combination of certain other technologies that has enabled us to be in a position where remote sensing satellite imagery is being used. The combination of data analytics and machine learning algorithms combined with unprecedented levels of satellite imagery being beamed down, combined with cloud supercomputing, be it Google Cloud or Amazon Web Services or Microsoft Azure, which you can put together, gives you insights like you would never have gotten before to solve the issues that are plaguing humanity today. And that's where we sort of wanted to come in. We realized that there's a problem with the current satellites, huge satellites, slow satellites that are being sent up, and that there's so many different applications that will need to be tackled with remote sensing. And our constellation will be able to access a unique data set that will help organizations make better decisions. For example, there's problems such as water pollution. Water pollution costs the United States alone about 4.3 billion US dollars every year. Or if you look at agriculture, right, 40% of global crops are lost to agricultural pests, and that's about $500 billion in lost revenues worldwide. How do we, like satellite imagery is one way to be able to tackle this. Or if you look at oil and gas leaks, 3.6 trillion cubic feet of natural gas leaks every year, and this is just in North America alone. This obviously causes a loss to the companies, but more importantly, it causes a lot of harm to the environment. And to be able to tackle these in time is what satellite imagery will be able to do. Here on the screen, you can see a couple of images. On the left is an image taken from a drone, but if you see on the right, you're able to detect that there's a natural gas leakage there, and you're able to go out and tackle that before it becomes a huge issue, because in most cases, there might not be people in remote areas that will be able to look at these. As I mentioned, we'll be able to look at changes that are occurring on the face of the planet almost every day, and these changes will enable us to make better decisions for the planet and for different businesses as well. The amount of applications that remote sensing or satellite imagery will be able to get is there's a whole host of other different things. Not just it'll not only enable companies and organizations to help make their businesses more efficient, like in the case of agricultural companies or oil and gas companies or mining companies. They can be also used to make the world a sustainably better place. Here you can see that scientists have already been using small satellites to save the world's coral reefs, which is becoming a huge problem. Or if you look at how satellite imagery in space is helping us save drinking water, we're able to look at where water pipelines are and be able to detect if there's any leakages depending on how the vegetation changes above ground. Be it stock picking to farming to being able to predict what the weather is going to be. There's a whole host of applications that you can do. So essentially, remote sensing has progressed very quickly from when it initially started. How it initially started was people used to send these capsules into space, and they used to have these tapes on the capsules. They used to take images, and then they used to recover the capsule through the means of a deceleration chute, which used to come down, and there used to be an air recovery through an airplane where they used to catch this capsule, take the tape, And from then we have come now to be able to be in a position where there's hundreds of satellites floating around the Earth that give us data of almost every geographical location at a 24-hour frequency. So the progress in just the past few decades has been immense and rapid. And it doesn't just stop there. Small satellites can also be used to send, take images of the resources on the moon, for example. Very recently, NASA also launched a couple of small CubeSats called the Marco CubeSats to Mars, where they're able to essentially demonstrate that you don't need huge orbiters and probes and satellites that cost hundreds of millions of dollars or years to make. You can actually build and deploy these small satellites very rapidly to any planetary body in the solar system, enabling us to go out and check these out at a much higher frequency than we have been able to explore it. Or be it sending small satellites to the asteroid belt to be able to detect which of these asteroids actually have ice or water or certain minerals that will be needed to be brought back to either the Earth orbit or the moon orbit for us to have in space resource utilization. So remote sensing has gone from just having certain tapes on certain capsules to now being able to deploy these small satellites to sense remotely what are available not only on Earth but on any other planetary body as such. So I think that's in brief what we are trying to do, and the applications are tremendous. Just in the last few years, we have gone from having tens of satellites that are able to take images of the Earth to having hundreds now, be it through Planet Labs or through our own satellites that will be going up early next year. That we're able to do this, and even though we are having hundreds of satellites today, we can just say that we are at the starting of what the actual potential of this data can be, because the data is coming down, but then to be able to use this and convert into real world insights is what needs to be done. So I think that's all from me. I'm happy to take any questions that anyone else has, or things like that. Again, thanks for having me, and it's been a pleasure talking about a field that I have a personal passion in.
Thank you so much, Awais. That was real crisp and brief introduction about remote sensing and its applications. And yeah, you have this concept of sending in micro observatory satellites into the Earth's orbit and creating a constellation out of it, and finding its application in regards to monitoring the unseen regions of the Earth. Can you explain us more about this particular concept, like how it works in the sense of from the deployment, like how are you planning to deploy all these constellations, like how many constellations will be sent at what stage, and how long, what's the duration of this project?
Yeah, so I think the one thing that we wanted to do, there were a couple of things we wanted to do. One was cover every geographical location, because that's something that satellites enable us to do uniquely. Once you have sent this asset up in space, you're able to take images anywhere, and you're able to take consistent images. And the second aspect to that is being able to get it as frequently as possible. In some cases, you might need images almost every 3 hours to every 6 hours. In some cases, you'll need it every day. And the thing that I mentioned was, from having these huge satellites that were able to only take images once a week or once a month, we are now at a position to be able to take it every 24 hours. So what the plan that we have is, we have a plan of sending about 30 satellites by the end of 2022. This 30 satellite constellation will provide global coverage every day. In that process, we have the first satellite built, tested, and ready to go. It was actually supposed to launch last month, but due to COVID, it's been pushed to early 2021. So just waiting for that. And a second satellite that we are building that will launch on a SpaceX rocket next year. So these are the two satellites where we are testing out the capabilities of what can be done, how small these can be made, and the timeline after that essentially is to have these 30 satellites that we will launch in 2022 or 2023. So I think that's the plan that we have.
Okay, and could you explain more about the launch part and the orbit that you are planning to place these satellites and something on it?
Yeah, so there's different. I'll take you through the entire process. You start with the designing of the satellite, as to how the satellite will be designed, what the camera will be, what the parameters will be, and then you manufacture it, and then you integrate it. You put the different parts of the manufacture together, and then you take it through a very stringent test regimen. After it's gone through certain tests that it can withstand certain vibrations, certain shock loads, then you put it on the rocket. You use the services of someone like ISRO, or you use the services of someone like SpaceX, and then you put this on that rocket, and they send it to an orbit that you want. In our case, we are going on a lower Earth orbit, which is 500 kilometers from the surface of the Earth. So remote sensing satellites are usually closer to the surface of the Earth compared to geostationary satellites, which are 36,000 kilometers away. Now, it doesn't have to be, and there's multiple different orbits that you can send them in. There's something called the sun synchronous orbit, where no matter what time you like, if I'm taking an image of, say, Delhi today, and the next time the satellite takes an image of Delhi, it'll be the same time. If it's taken at 12 noon today, it'll take it at 12 noon tomorrow. So it's synchronized with the sun. So there's a sun synchronous orbit. There's also something called an polar inclined orbit. If you want to concentrate on a particular geographical area like India, you put it on such an orbit that the focus of the frequency is over India and not over other regions if that is not your priority. That I think would be the thing. We design the satellite, we manufacture it through different partners, we put it together and take it through a very stringent test regimen. And then we look at who can launch this satellite for us. It's almost as easy as finding an Uber nowadays. You reach out to different rocket providers, you ask them what's the cost, what's the timeline, can you accommodate a satellite of this size. And since we are building small satellites, it usually becomes much easier. Once it's up there, it usually takes about a couple of weeks for us to get the early stage of operation sorted out, to be able to first track the satellite, see if everything is working properly, be able to communicate with it, after which it can start beaming down the images that it's supposed to. So I think that would be the brief journey.
Yeah, as okay, this is how far as my knowledge goes too. Like when we place satellites in the orbit, we need tracking centers there down on Earth, like at different locations. So for the constellation that you are planning to place in, is it necessary that you have tracking centers like spread across the world, or is it okay that you have only one tracking center for the satellites to looking for their operation?
So it depends on what you want. You can make do with one. I mean, you need at least one ground station for you to be able to communicate with the satellite, unless you like plan to go out and bring that back like they did earlier with the shoots that I mentioned, right? But in general, just one is enough for you. The problem with just one is you'll have to wait for that satellite to come across the ground station. So it gives you limitation in terms of how frequently you can communicate, which is why there's multiple different organizations coming up that have ground stations spread across the globe, from North America to the Pacific Ocean to the Atlantic Ocean to whatnot. We personally have partnered with an Italian company called Leaf Space. They have ground stations in Europe, in New Zealand, in the US, and everywhere, which gives us many more opportunities to communicate with our satellites. However, all those are not needed if we just want to communicate with it, 2 or 3 times a day instead of 16 times a day like we want to do now. We could do it with just one ground station as well. But in most cases, there's also another way of sort of doing it. If you have just one ground station on the North Pole, very close to the North Pole, or very close to the South Pole, almost every orbit will pass through the pole, which means that even if you have one ground station, you'll be able to communicate with it multiple times a day. So that's the different ways of in which you can operate with the ground stations.
And regarding the equipments that go on board on the micro observatory satellite, what all kind of equipments are being placed on it? Like, what is it just the image data that you're trying to gather in, or are you just looking in the visible spectrum, or is it being planned in a different spectrum, or is it just the IR spectrum or a particular regime that you're looking into?
So the main focus of the satellite is the camera itself that we are looking at. It's going to have images in the infrared range as well as the visible range. So you'll be able to see the red, green, and blue bands that your normal eyes are able to perceive, as well as a few bands in the infrared range that will enable you to see certain things like what is the water content on the leaves of the crops, It'll enable you to see the natural gases that your eyes cannot see, for example, things like that. But we also have other, supporting equipment on there. You need to have equipment to support the control of the satellite. If you're taking images, the satellite needs to be very stable, pointing down towards the earth for you to be able to do that. We also have onboard processing solutions, because the images we take are usually very heavy, and we have limited time in which to beam them down to the ground stations. So you need to be able to compress them, and there's also ways in which you don't need to beam down the images at all. An example I could take is, if you just want to know what the number of ships over a particular sea was, you just have an algorithm running on board the satellite itself, which counts the number of ships that are there, and just beams down that number, which is a very few bits, and which you can do very rapidly instead of beaming down multiple different images to do that. So that is what we have on our small satellites. We are focusing, the satellite is optimized to work for the camera that we are looking at, but it has supporting equipment to make sure that we are as optimized to the focus and the priority that we have.
Okay, your take on the upcoming satellite technology that the world is going into. Like, there are multiple startups that are looking in for developing CubeSats, and we're all going towards the miniature version of satellites, as you pointed out in the presentation. Like, from the hefty satellites, we are moving towards the miniature ones, and we're also looking in for sending these satellites in their miniature form to Moon and to Mars as well. So, your take on it?
So I think there's a limit to which you can miniaturize imaging satellites or remote sensing satellites, because when you're looking at the cameras, you have optics, you have sensors, and there's certain physical limitations to the optics. You need to have certain focal length, you need to have certain size for this optics or mirrors for you to be able to get images of good quality. So you can't keep on miniaturizing it forever like you could do with just IoT satellite. So we are almost at that edge now in which you can't miniaturize it anymore, because the limitations of physics for the optics or the cameras won't allow it. That said, we still are lacking many different types of imagery or data sets that we need to beam down. If you want to look at something like NASA did, which was the soil map, moisture, and SMAP, for looking at what the soil moisture is. That's a very important data set that's needed for global agricultural usage, but usually other satellites don't have it. Or if you're looking at synthetic aperture radar data, where you need radar to penetrate the clouds instead of having passive camera, that's the kind of data set that's needed. Or if you want thermal imagery, we are going longer and longer towards the infrared range to be able to see the heat signatures for the plants, the dust, the water, and whatnot. So, one satellite can't cover the entire spectrum. You will need different companies working together, and it's not just the data. I mean, I think in 5 to 10 years, satellite imagery will get commoditized. It will become very easy and very inexpensive to get satellite data from multiple companies that are coming up. It's how you make use of the data and whether the data is actually useful for analysis, where you can take this data and extract insights, is where things will become useful. So I think that is where the industry is going. As I said, we're still, even though we have hundreds of small satellites up there, we're still at the initial stages of this technology and usage, and the next 5 to 10 years will be very interesting to see.
Okay, there are a few questions being asked by our young students on the YouTube chat. They want to know about, the cost of manufacturing these satellites, how the cost would vary from the huge satellites which ISRO manufactures to the satellites that you are proposing right now, how the budget varies. So they basically want to know about the mission project.
Yeah. I think if you're looking at 10 years ago, to have the kind of imaging satellites that we are doing would have cost about $20 million. That's what 140 crores, almost 140, 150 crores. Now you can do it in about 10 to 15 crore rupees, right? So like the cost of manufacturing this has come down by tenfold. And like the cost varies depending on the type of imaging you're doing. If you're looking at much higher resolutions and much bigger satellites, you could spend anywhere between 14 to 50 crore rupees. Or if you're looking at smaller satellites, you don't want such high resolution, it could be done in about 2 to 7 crore rupees as well. So it depends on how robust you want to make the satellites, how long the lifetime needs to be, so yeah, I think that would be the general cost. It varies depending on the use case, but from at least 10 to 5 years ago, the cost has come down tenfold. What would have cost 140 crores to do the same kind of imaging would now cost about 14 to 15 crore rupees.
So, what is the life expectancy of these microsatellites? As we are looking in for a low Earth orbit, they usually suffer from tractions, and in a period of time, they would even fall back to Earth. So, with
Yeah,
respect to that.
absolutely. So I think the biggest problem for the lifetime is the aerodynamic drag. So even if you are at 500 kilometers, there's a bit of atmosphere which leads to drag, which means there's an orbit decay. So if you are at 500, it keeps on decreasing to 475, 450, and the closer you come, the faster that decay becomes. The lifetime of our first satellite is about 2 years, and that's because it's a proof of concept satellite. However, the ones that we will be designing for the constellation are about 7 years of lifetime. And there's a couple of ways in which you can have the extended lifetime. You can have radiation hardened components, because one big problem is cosmic rays and other radiation bombarding your electronics, leading to some sort of a loss of power or loss of computing. The other way to be able to do that is to have thrusters on the satellites, because as and how your orbit keeps decaying and coming down, you can use these thrusters to push it back up and do something called the station keeping. So that would be the lifetime of satellites and how you can sort of extend that from 2 to 7 years.
Okay, one of the students here from YouTube, they want to know how the onboard power system works for a microsatellite. Like, do they carry fuels, or is it just the solar panels that power them, and how efficient are they?
Um, so the solar panels for the satellites, there's a specialized industry for building solar panels for space, because they need to be very, very efficient compared to on-ground systems, which also means they're usually very expensive. You need about 30 to 33% of efficiency in these cells, compared to 10% or lesser that you usually have. And one of the issues we faced is you're not able to get them here in India. No one makes those cells here, so you have to procure them from Europe, for example. And the only source of power that your satellite will have are also the solar panels up there, because once you can have the batteries charged up and sent, but then they're going to get depleted after a while. So you need solar power from the solar panels to keep doing this. And a major chunk of the work on the computer of the satellite is also to have a sun pointing mode, which is essentially pointing your solar panels towards the sun to get as much power as possible. So I think, yeah, the solar panel and solar cell thing, people are trying to make it more and more efficient year on year. Because apart from nuclear thermal generators, which people use for long deep space missions, every other spacecraft or space mission needs solar panels.
Okay, this is the last question I'm going to ask you. The Pixxel motto says, "See the unseen." Your take on it?
So I think seeing the unseen is because when we started out, we were looking at solving different problems or issues. Some pictures are showed in the presentation as well. We were trying to look at the natural gas leakages that were happening from oil and gas pipelines. But any open source data or even commercial data at the time was not able to detect these issues. So we needed something much more information rich or information dense kind of a data set for you to tackle that. Or if you're looking at agriculture, what you can do with satellites today is you can take a look at the crop health status, soil health status, and whatnot. But if you're trying to go a step beyond that, which is identify how the soil nutrient content is, whether there's NPK deficiency, whether there's an deficiency in nitrogen, phosphorus, or something else that you need a fertilizer to do, or you need to identify what specific strain of pest infestation or crop disease there is. Those are the kinds of imagery you can get with thermal infrared imagery, shortwave infrared imagery, and whatnot. So that is what we wanted to plug. Like, there are problems that were literally unseen from today's satellites, which we wanted to be able to plug the gap with our satellites, which is where seeing the unseen comes in, because our satellites will be able to help see certain problems that people were not able to see till date.
Thank you so much for that informative session on remote sensing and talking all about the Pixxel and your project. And it was a great pleasure to have you here with us on the World Space Week celebration at SSERD. And I hope all of the viewers also enjoyed and learned a lot about Pixxel and also the startups. Like, they all are motivated. I can see here on the chat, and they all have been motivated with the concept, the way you approached and came up with the concept of Pixxel and looking in for solving the problems around the world by sending in micro observatory satellite. Thank you, Awais. Thank you for those wonderful words. And uh, we have another keynote starting right now at 5:30, and it is by Professor J. Srinivasan. And it is on understanding weather and climate through satellite. The, join link session is uploaded on the platform. And I thank you all for joining in for today's session, keynote session on remote sensing. Thank you all. This is Tejas signing off.